Nice to see these here. I look forward to reading them. So today is a fun topic. We're going to talk about nonlinear regression, and in particular, neural networks as a way of doing that. And neural networks is an interesting subfield of machine learning. It's been around for a long time, since the 1980s. And actually a little bit of history in machine learning. It was sort of a dominant approach to doing machine learning for much of the late 1980s, the early 1990s. And it was around the late 90s that probabilistic models, like graphical models that we've talked about here, became much more popular, and they kind of eclipsed much of the work that was going on in neural networks. Although many of the good ideas from neural networks were imported into that. But recently, neural networks have had a kind of resurgence in some ways, for reasons that I think might become clear during this lecture. So let's just start in. I think, by the way, of neural networks from two views. One is, in terms of this course, we've talked about regression problems as being just function approximations. We're trying to learn a function from x to y. And when we say regression problem, what we mean is that y is a real valued number. And the approaches we've talked about, like linear regression, assume that y is a linear function of x. But in many cases, of course, we don't know what kind of a function of x, y is. And artificial neural networks are a great way to do regression when we have that kind of a problem, where we don't know that it's linear. It's probably nonlinear, but we don't know exactly what it looks like. We can't say for sure it's a third-order polynomial. So we have to just use something that's very expressive. That's where artificial neural networks come in. So that's one of the two ways I think of what they contribute to the field. The other way I think of it is, if you think about what we've talked about in this course, it's primarily function approximation or estimating probability distributions. Those are the two things we've really talked about in the course. But I think of neural networks as a way of getting at another key problem in learning, which is, how do we learn representations? So for the most part, we've assumed we knew how the data was represented. It's some feature vector, x1 through xn. And we think about, given these representations that we know, how do we learn the function? But one way to think of neural networks is they're a way to learn representations, re-representations of the input data that are valuable in all kinds of ways. So that's another way I think of the field. So let's just jump in. To be precise, here's the definition of an artificial neural network. We're trying to learn some function from x to y. And in our case, x can be a vector of any kind of inputs we like, x1 through xn. And y can also be a vector of any kind of outputs. So now we're not talking about predicting a single variable y, but a whole vector of them. For example, y might be an image, a photograph. And we might be predicting what image the robot will see, given the image that it sees now as input. What image would it see if it drove forward 3 meters? In fact, I've trained a neural network to do that with a robot and a camera. It was kind of interesting. So once you get into the idea that we're learning functions over vectors, that the input can be a vector, but so can the output, then you realize we can use this to predict images or all kinds of data that has a much richer structure than a single scalar, single variable. the function itself that we're trying to learn is represented by a network of logistic units, which are used based on exactly the same function as our friend logistic regression. And in fact, when we train a neural network, we train it to fit the input and output vector, and we use gradient descent to minimize the sum of squared errors in predicting the outputs from the inputs. At least we do that if we want the maximum likelihood estimates of the weights. And if we want map estimates, then we also add in a term for penalizing weights. So the cool thing here is that it's building up on the building blocks we've already talked about, like logistic regression uses the same function, and all the things we said before about linear regression and what it meant to do maximum likelihood estimate or map estimate. Of course, if we make the same kind of assumption of the probabilistic model, then we get the same kind of objective that we tried to optimize. So let's look at a neural network. Here's a nice example. This is a neural network trained to recognize different vowel sounds. Okay, so the input, which is encoded by just two features, F1 and F2, encodes a sound like the vowel that you hear in the word hood, hid, had, head, etc. So different vowels there. And it encodes the input by the frequency, the first formant and the second formant, which have to do with power spectrum of the frequency of the sound. And so these are common features used in speech recognition. So you can think of every sound being converted to a point in this two-dimensional plot. In fact, if you can read the tiny font, you see that those points have different shapes, and they represent the vowels in head, hid, had, hood, have, heard, heed, hud, etc. Okay? Now, in this neural network, there are two layers of logistic threshold units. Here's a unit, for example. That's the output of it, and it has these two inputs. And the output of that is a value, a single real value, which is the output of the logistic function, which takes these two things as inputs. And these two edges represent the weights on those two inputs for that particular threshold unit. Okay? Its output, however, becomes the input to the second layer of logistic units. So, for example, this one uses the outputs of all of these. Some people call these the hidden units because they're in the middle of the network. They're not really pinned down when you specify the input to the network. So the second threshold unit uses the outputs of all those first layer units and multiplies those by its weights on those black edges to get its output. And as you can see, there's an array of 7 of these first layer logistic units, followed by an array of different output units. As many output units as there are classes in this classification problem. We're trying to classify the sounds according to the vowel sound that you hear in hood, had, etc. And so in this case, the output is being coded as a vector with all zeros except for a single one. So that would be the output that represents this particular vowel sound. So each of these outputs is essentially representing a particular vowel sound. Okay, so in this case, the output vector is just a bunch of zeros with a single one. At least that's what we train it to be. Once we train it, of course, then the output numbers might not be exactly zeros and ones. They're output of logistic functions. And so we just round up or down to 0 and 1 in order to see the closest coded word. Okay? Now, also in this picture, what's interesting is the decision surface learned by this neural network. So that's what those regions are. That's what these lines are on this plot. So as you can see, this is a very nonlinear decision surface. Inside of each of these regions, like this region, is one particular category. Okay. So this particular network, once trained, all the inputs that fall into this red circle will correspond to, which one is it? Yeah, head, the first one of those. And so you can see what I mean when I say this is a very nonlinear learning mechanism. And you can kind of imagine why. It's that we're putting together these two layers of logistic functions. It seems like kind of, a single logistic function has an output that goes like this with respect to the weighted sum of its inputs. Now if you take those and put them into a second layer, you have a lot of flexibility in terms of how you can carve up the input space. Okay, so there's a prototypical neural network. In fact, most neural networks that I have seen or used myself have this general kind of architecture where they're essentially two layers of threshold units, and therefore one hidden layer, the output of the first. So we have the input values, the output values, and then the output of the first collection of threshold units is the hidden layer. And in this one, they're all the hidden units are completely connected to all the inputs. All the outputs are completely connected to all the hidden units. And so it gives a lot of flexibility. Okay, let's look at another one. Here's another one of my favorite early neural networks, which kind of revolutionized the field of autonomous driving. And this is due to, due to Dean Pomerleau, who was a PhD student here at CMU, went on to become a faculty member and then went on to form a successful company that watches the road in front of you while you drive and sounds an alarm if you appear to be driving off the road, which was acquired a few years ago by a larger company. And so what was Dean's thesis research about? He trained a neural network to steer a car. And so what he did was he had a car with a camera here looking out the windshield. And that camera image would see something like this. And then he trained a neural network to use each of the pixels in the image as an input. And as output to encode the direction that the car should steer to stay on the road. And he encoded it with numbers that made it kind of like this. So he would encode it not exactly with all zeros and ones, but where there were real valued outputs that would peak at the direction you should go. And this worked. The way he trained it is he went out on Route 28 north of Pittsburgh. If you've ever been on Route 28, you know what a scary idea that is. And early on Sunday mornings when there wasn't much traffic. And he would drive the car himself. That's how he collected training data. So the car was instrumented. Here's the camera image. Here's the way Dean was steering. And then once it was trained, he would just sit there and let it steer itself. That's the scary part. And it worked. And this car drove essentially 50 miles an hour, successfully tracking the road based on a neural network. By the way, one little trick he had to do to make it work was the way you probably drive, we'd get a lot of positive examples, but not very many negative examples. And so one of the difficulties in training the neural network, when he first tried it, he had basically positive examples. And the problem is all of the images on which it was trained. Think of P of x, not P of y given x, but think of P of x. So he was driving on the road. So all of the inputs, images that he was training on, represented what you would do if you were right in the middle of your lane, because that's where he always was. But he didn't have any training images that showed what you should do if you were over on the shoulder somewhere, which, of course, during early training, the neural network would end up on the shoulder, but then it would have no training examples that showed it how to respond to that. So one thing he had to do was essentially synthesize some perturbed training images along with the corresponding steering commands to make this work. But it did work, and it really did. It was a big turning point in research on autonomous driving, which has come a long way since. Now, one thing that's interesting about this neural network and gets at what I meant when I said that I think of neural networks as a way of learning representations, is that once the network was trained, we could look at any of these units, any of these threshold units, and we could ask, what are the learned weights? And so, for example, if we look at one of these hidden units, let's say this one, which of course has an input from each pixel in the image, and if we ask, well, what are the weights that that hidden unit learns when it's trained, when the network is trained, the answer is here they are. These are the weights of one of the hidden units. And the weights are plotted where white means a large positive number, black means a large negative weight, and gray means a weight close to 0. And they're plotted on the same, on the image plane. So this weight over here corresponds to the weight associated with this pixel in the image. And this one corresponds to this pixel in the image. Get it? So you can look at these weights and you can see these kind of bands of regions in the image that have high positive weight, meaning if the image is light, if the intensity is high positive, meaning a white pixel, times a large positive weight, that's going to activate the output of this unit a lot. Whereas if it's dark black, it means if the image is white there, you're going to multiply it by a large negative weight and deactivate that unit. And so when I look at this, I don't quite know how to interpret it, but it reminds me of this kind of geometry of the road disappearing perspectively before you. And Dean thought this had to do with it finding essentially how that road before you looks. So if you imagine, you know, putting this particular road on this image and then pushing it over to the left or to the right, you're going to do something interesting with that combination of weights. So it's not always easy to see what those weights mean, but here are the weights on the output unit. Or sorry, to the output unit from that same hidden unit. So these are the weights into one hidden unit. And these are the weights from that hidden unit to an output unit, to the output units. And you can see what this hidden unit is doing is it's going to, if it's activated, it's going to, if it were the only hidden unit that was activated, it would cause that output vector to have values kind of like that, which means it's going to recommend that you steer to the left. And so I don't quite know how to make sense of that, but maybe if the light road The road is actually lighter than the background. So if the light road is over here, it's going to give you, I don't know how it quite works out. Okay, so there, yes?
I'm just curious. Can you read it from in the middle of the road?
No, he drove in the lane.
But you see that picture? The white line is in the middle.
Yeah. This is an artist's conception. This is not an actual photograph of the road. The actual photograph is what you see out that windshield. It's messier.
Route 28 looks a little bit like this.
Right. So over time, he developed various versions of this, including he found that if you wanted to go off on an exit, once the system was trained to drive on the road, it wouldn't go on exits. It would just go on the road. So he had to learn another neural network that would learn, if it was invoked, it would take the exit. So then he ended up training collections of neural networks and trying to get something that would take some commands about how to switch back and forth. And it got fairly elaborate. But the amazing thing is that the dog can dance, right? So the amazing thing is that something this simple actually works. Okay, so neural networks. A lot of the work in this field originally was motivated and came from researchers who are also interested in cognitive science and how brains work. And in fact, one of the interesting things about brain, here's some interesting cocktail party facts about brains that are interesting to know. So for example, the neurons in your brain take at least a millisecond to switch their state. They actually spike, but basically, it's hard for your neurons to go from spiking to react to anything in less than a millisecond. So roughly speaking, the switching time in your neurons is a millisecond. Pretty slow by computer standards. Furthermore, you have 10 to the 10th of these in your head. It's like, what's that, 10 billion? Each one of those neurons is connected to about 10 to the 4th or 10 to the 5th. It actually depends on where the neuron is in your brain. But, roughly connected to another 50,000 neurons. So it's a very interconnected network. And it takes you 1/10 of a second to recognize your mother in a photograph. Actually, it takes you 1/10 of a second to recognize me in a photograph. Although I'm sure your mother is much more important. So, but the thing is, anything that you can do instantly still takes you 1/10 of a second. Okay? But you can do it in 1/10 of a second. So now, if you think about that, if you can recognize your mother in a photograph in 1/10 of a second, and it's taking your neurons minimum a millisecond to change state, that means you couldn't possibly be using a chain of neurons more than 100 deep for something as sophisticated as recognizing an individual person in an image. So that's a pretty short sequence of computations, 100 at most, and to do something that sophisticated. And I defy you to come up with a computer program that in 100 steps could look at a photograph and recognize each of us, which you can do. So based on that, a lot of people suggested, well, there must be a lot of parallelism in the computation that's going on. It's not that you only have 100 flops. It's that they're only sequenced 100 deep, but they can go very wide. Okay. So, and in fact, that's very much what people assume these days is the basis for neural competition or neural computation. So a lot of the original motivation for artificial neural networks was, well, if that's how the brain does it, then maybe building these parallel collections of thresholded units and assembling them and training them to get the right weights is also a good way to try to get computers to operate. All right. So you already know pretty much what you need to know to understand neural networks in 10 minutes. And so we're going to do that. And then we're going to talk about some of the more interesting properties and research directions about neural networks. Okay, so I mentioned each unit is a threshold unit, which is a logistic function. That's shown here in great detail. But the output is just, given a collection of inputs, x1 through xn, our output is just the logistic function where this intermediate variable called net is just a linear weighted sum of the inputs. Same logistic function you know. And these neural networks are built out of those. To review what we said about linear regression, when we tried to build a probabilistic model for linear regression, we said, well, what if we assume that the y we're looking at is some deterministic function of x plus some zero mean Gaussian noise? If we do that, and then we ask, how do we maximize the conditional data likelihood, the conditional likelihood of y given x over all of our training data, we agreed the answer was we'd want to minimize the sum of squared errors between our predicted output y and, between the training example value of y, the true output y, and our learned function's prediction of what y would be. And that's exactly what we do when we train neural networks. Okay, now notice it's not quite the same as what we were doing when we trained logistic regression, because there we were assuming our output y is a Boolean random variable, and we were training logistic regression to get the probability that y will have the value 1 given x. Here we're treating y as a real valued variable. And so just like in linear regression, we end up with a different objective to optimize. We end up with the same one we get for linear regression, not the same one we had for logistic regression. But you see why. It's because we have a different probabilistic model. Okay, so we can train neural networks that way. And in fact, if we want to get not maximum likelihood estimates, but map estimates, then we can furthermore say that we could put a prior on the weights of the neural network. Maybe we put a prior that the weight will be centered around 0 with some other smaller probability that it'll be non-zero. And then we end up with this modified objective function, the same one that we had for regularized linear regression. Okay? So it's really the same thing. So if you want to derive the learning rule for a neural network, you want to basically optimize the same objective that we did for linear regression, except now you have a whole lot of weights spread across a whole lot of threshold units, and you have to simultaneously solve for values of all of those weights and all those threshold units that are going to optimize this objective. So to do that is actually not that hard. You can calculate the gradient and then do a gradient descent search. Here we see the calculation of the gradient for a single logistic function if we're trying to minimize the squared error between the target output, that's the training, and the target output is the training signal and the observed output of the unit with its current weights. And here we get a gradient, and I'm going to go. I'm putting all this detail on the slide so you can go through the details if you like. But it's the same kind of derivation we've done in the past. You can do it again yourself. In fact, you probably should do it without looking at this slide if you want to test yourself and then come back and look at the slide. But it's the same kind of thing. If we want to train a neural network, what we're going to do is we're going to derive a gradient descent rule to optimize to, at each step, change all the weights of all the units in the network, and then recompute the gradient and do that again. And what's shown here is just what we would do if we had a single threshold unit. In fact, if you have this kind of two-layer hidden network of units, then the gradient descent rule gets a little bit more complex to do the gradient descent, but it's still very, oops, let me look here. It's still very straightforward. So if you work out the arithmetic, and it's in the readings, if you want to look at it, the gradient descent rule boils down to this. And so I will go through this, and you'll see that it makes even some intuitive sense. Okay, so, and this gradient descent rule is called the back propagation algorithm for training neural networks. So here's a typical network off on the right, and we're going to use this notation that X is our input, T is the target output. By that I mean the training signal. O is the observed output of the network itself, its prediction. And Wij is the weight from unit I to unit J. Okay, so now what does this say? First of all, we're going to initialize all the weights. We can initialize them to anything we like, but in fact, to tip our hand, there are severe local minimum problems for optimizing the weights in neural networks like this. Unlike logistic regression, which has this nice convex objective, the objective in neural networks is highly non-convex. It has lots of local minima. And so when we do gradient descent, the best we can guarantee is that we'll fall into at least one of the local minima. And so it does matter how we initialize these weights. And nobody knows how to do it perfectly, but the most common strategy is to initialize all the weights to very small numbers close to 0. Okay. And now we begin the gradient descent loop, which is for each training example, we input that training example to the network and we compute its outputs. And then we're going to take a gradient descent step based on that one training example, which means that for each of the outputs, we compute this term called delta, which is, this is a term where essentially O is the observed output of the network and T is the target, that training target. And so you see there's a term here that essentially is looking how far is the output O of the network from the training signal we're trying to match, T. And the bigger that difference, the bigger this error term. These other things here happen to appear because of the form of the derivative of the sigmoid function, the logistic function. But the thing that makes intuitive sense here is that we have an error delta. We're going to call this the error delta for unit K, which is proportional to how far apart the true value Tk is from the output of that unit. And then for each hidden unit, we're going to calculate an error signal for it. Like here's a hidden unit. We're going to calculate an error for it, which is a weighted sum of the error units on these output unit Ks. And so for the hidden unit, what we're going to do is we're going to essentially attribute, we're going to allocate the error at each of the outputs according to some weight to hidden unit H. And what weight are we going to use? Well, we're using the weight between unit H and unit K. So if this is unit K and it has some error delta K, then we're going to pass on some of that error for the purposes of training this sigmoid unit. And how much? Well, depends on how much its output depended on unit H. So that makes sense too. It's a kind of, if output K is wrong and H has a heavy weight going to output k, it has a strong influence on it, then if it was wrong, we want to somehow change hidden unit h also. And this just falls out if you work through the math of the gradient descent rule. And again, here's this thing that has to do with just the derivative of the sigmoid function. And then we just update every single weight in the network. From every unit I to every unit j, we update it by adding in some term which corresponds to a step along the gradient. And that term is just based on how strong its input I is. So weight wij is from input I to output j. So it depends on how strong its input is, how big that delta error term is that we assigned it, and some learning rate. So intuitively, it's a very sensible thing. It's also mathematically exactly what you get if you derive the gradient descent rule for minimizing the sum of squared errors at the output units of the network. Okay. So that's all there is really to the back propagation algorithm. One detail that I kind of jumped over, but maybe some of you caught, was, remember when we talked about gradient descent for logistic regression, we said, well, we could do this. When we introduced it, we talked about doing it by looking at all of the training examples, calculating the gradient with respect to all of those, and then updating the weight. But here, that for each training example that's talking about taking a gradient descent step based on just one example. And in fact, that's a standard idea for doing gradient descent more efficiently in many problems. So there are really two different algorithms for training neural networks, or in generally for doing gradient descent. We might call one of them batch and one of them incremental. Many people call the incremental one stochastic gradient descent. But the proper definition of gradient descent is that if we have a set of data, if our data is D, is the set D, then the proper way to do gradient descent, of course, is to compute the gradient with respect to D and then update our weight, and then come back and look at D, the set of all training examples again, and update it again, and look at all the training examples again. But if you have a lot of training examples, thousands, then that's a lot of computation to get the gradient. And so the idea behind this incremental or stochastic gradient descent is if you instead just pretend that, just look at one example at a time and calculate the gradient with respect to that one example, little d. And then after you take that gradient descent step, when you take the next one, you pick a different example. Then you end up with, and if you take small enough steps, then you could see that when you add up all the gradients with, suppose my data set D had 1,000 examples, I could either use them all and compute the gradient and take a step in the correct steepest direction of the gradient. Or I could, for the same amount of computation almost, take 1,000 steps, one each for each of the training examples. But of course, each of those steps I take won't really go down the steepest direction with respect to the fold gradient. It'll just be sampling some subset of the data, one data point, and taking a step. And so if I make my learning rate small, so that I'm taking only little steps, you can see that, in fact, you can prove that if you make it as the step size, the learning rate approaches 0, then these two approaches become equivalent. But basically, the intuition is you can have a more efficient algorithm that takes downhill steps but not steepest descent steps. And if you sample the training examples, compute the gradients, and take those steps, generally that's not as provably correct, and provably you're not going in the steepest direction of the gradient, but still taking 1,000 of those steps instead of just one perfectly correct step can usually be a better thing to do. So you should know about that idea in general, not just for training neural networks, but anytime you want to fall back on what I consider to be the generic weak method for training machine learning systems, gradient descent, you should be aware that there's this efficiency issue, a trade-off between whether you compute the proper full gradient, which could be costly because you have to sum over all the examples, or whether you just sample a subset of those training examples and compute an approximation to the gradient. And then doing this incrementally, one example at a time, is an extreme point on that spectrum that you could trade off. Okay? All right, so that's training neural networks. And so then to kind of summarize, we're doing gradient descent over the entire vector of all weights of all the units at once. So every one of those gradient descent steps, we're updating every single weight of every single threshold unit in the network. And then, in fact, this works not just for these fully connected two-layer networks, but any directed acyclic graph that you construct. You can easily use the chain rule to derive the appropriate gradient descent algorithm for. So you can make your own boutique designer graph, directed acyclic graph neural network, and train it. One pragmatic thing, people often, because of this problem that the error function we're trying to optimize has many local minima, and therefore if we, so this would be like the vector of all weights, and this might be the error, the sum of squared errors that we're trying to minimize. And so if we start with some particular weight, we might do gradient descent and end up here. That might not be the best local minima, but what gradient descent is going to do is put us into a local minima. And so people have a lot of heuristics for trying to avoid local minima. One of them is just train your neural network 100 different times with different initial weights, and then pick the final one that has the lowest training error. Maybe not a bad idea. Another one is to add what people call a momentum term. This one always struck me as a little odd, but I have to admit, in practice, it's often helpful. And the idea is this, it's sort of like you think of gradient descent as your weight is moving down, down. It's sort of like a ball rolling down the hill, except that it's a momentumless ball. When you get to the bottom of the hill, it just stops because now the gradient's uphill. You're not going to take a step there. So this heuristic, called momentum, is to effectively simulate the ball rolling down the hill with momentum. So when you get to the bottom and the gradient is 0, instead of stopping, you calculate your next step based on at iteration n, you calculate the weight update based on that training rule we just discussed, but you also add in the update you made on the previous time step, previous iteration update to the weight. So in other words, you keep, if you added delta to it last time, and now the gradient is 0, you still kind of move in the same direction as the delta you talked before. So you blend the current gradient with the direction of the previous one. And the motivation or the argument I've heard, which I always found puzzling, was, well, then, you know, if you have a little scenario like this, it's good because you roll down this steep hill. Now you're going to make it up over this and get down into here. And people tell that story with such authority. And then, of course, it doesn't take long for you to point out that, well, yeah, but, you know, what if the error surface looked like this? And you come rolling down this hill, and now you make it to that one. That's not as good. So, so I don't quite, so I call it a heuristic. And nobody fully understands the shape of these error surfaces, but that's a common heuristic too. Did I see a question here before? Or did it go away? Okay. All right, so there are a lot of heuristics for how to try to avoid the local minimum problem in training. I thought it would be fun to show you some actual data from training one of these to give you a feel for how many gradient descent steps it takes to actually converge. So here's a plot, two plots actually for two different neural networks. This one shows the error of the training error and also the error on a separate validation data set as a function of the number of weight updates, the number of gradient descent steps. So as you go, so initially the training error is pretty high. So is the error on the separate validation set. And then as we start doing our gradient descent steps, of course the training error goes down monotonically, right? That's what we mean by gradient descent. It's guaranteed for the training error to decrease monotonically. But as you can see here, there's an overfitting problem because the error on this separate validation set goes down for a while and then starts going up. Here's another one in which, of course, the training error again decreases monotonically. And in this case, the error on that separate validation set is, well, you can see. I don't know how to describe it. Okay, so one thing that we have to worry about with neural networks, there's so many parameters we're estimating, it makes overfitting a serious concern. Often you can perfectly fit the training data with a big enough neural network and then do just terrible on the next test example that you're given, different from the training data. And so how would you deal with this? You guys are experts by now. You know how to deal with this.
I can think of this analogy between decision trees and neural networks. And this you talked about Occam's razor and the tree with the lowest, the decision tree with the lowest depth is usually a good approximate. Is usually good for thing. So there might be this thing that the neural network with the lowest number of units could be could have go over.
Good. So the suggestion here is maybe an analogy with decision trees where we saw a similar overfitting problem as we grow the complexity of the tree and then we end up pruning it back to something small. Maybe we could do something similar here and say we want the neural net with the fewest number of units. People have tried that and have found that it's hard to make that work. I think because you also have the question of the topology of the graph to consider. So unlike a tree where you know it's going to be a tree, in this network you don't know which unit to pull out and stuff. So in fact what people often do is they look at this other data and they say, oh, well, clearly here's where we want to stop training. Right? If I showed you that and I said, you know, this horizontal line represents, each point on that line represents a different neural network. They all have the same structure, the same graph, but they have different weights at each point in that horizontal line. And if I asked you, which of these neural nets would you most want to use if I'm going to give you yet another example and it's got to get it right, you'd probably pick the one right there because that had the smallest error on the test set and anything that it was doing beyond there to improve its performance on the training set was really counterproductive in terms of performance on the test set. That's overfitting. And so one common way to deal with this is you want to train your neural network. I give you 1,000 training examples. You say, okay, I'm only going to train on a subset of these, maybe 800. And I'll keep 200 aside. I'll do my gradient descent using those 800. I will have my computer program plot these two curves. It'll use those 800 that I chose to train. It'll keep the other 200, won't use them for training at all, but it will use it to plot this other curve. And then when it's all done, how does it know it's done? Because either it got down to 0 training error, or the test error started increasing, in which case it decides to quit. And then it just goes back to the log and says, well, okay, here's where I achieved the smallest test error. And so I will use the neural network stopping training there. So that's probably the most common way of dealing with this. Yeah?
That wouldn't work on the second graphic, because you would go down and then your test error would start increasing and you'd fail.
Yeah, good point. So this second plot is in here just to show that that method is fallible. So if we stop training as soon as the error on the test set started getting worse, we'd be misled in this case. And so when you implement this in practice, you usually go, some substantial distance beyond when it starts going up, just to make sure it's not going to go down again. And you can't really be sure. So again, it becomes a heuristic in the end. We know, by the way, of course, that the training error is going to decrease monotonically with gradient descent steps by definition of gradient descent. But we don't know, and we can't characterize in general what's going to happen on the test data.
There's not a guarantee unless you have the step minimum if the infinitesimal is small.
That's true. Good point. So even what I said isn't quite true, because if the learning rate is too high, so that we take a step that jumps across the valley onto the other side of the hill, then we can get into little oscillation problems, right? So if I'm coming down here and I take a step of this size and I get here, take another step of that size, I might jump across the valley. Of course, once I do that, then I'm not going to continue up the hill. The gradient is pointing down, so I'm going to jump back across the valley. But if I don't shrink my step size, I could just keep bouncing back and forth across. And so another common strategy is, as you increase the number of gradient descent steps, you also often shrink the step size so that you don't get this bounce across the valley problem. That's a good point. Was there a question here?
So previously we saw regularization terms that penalize excessively high weights.
Mm-hmm.
Would something like that?
Yeah, good point. So the comment here was, what about regularization? We used that before. And that's a great idea. And it's widely used. It's the most widely used idea for avoiding overfitting in neural networks. And that's why, remember at the very slide number 3, we said, here's what the MLE would be. We'd minimize the sum of squared errors. Here's what the map would be, the regularized version. We'd minimize an objective that had sum of squared errors over the training data plus the square of the weight vector. So we're penalizing for large weights. And that's another thing that kind of comes back to this comment about make the decision tree small. In our case, it's sort of like make the weight magnitudes small. And there's some interesting thing there, too. If you look at the form of the logistic function, there's so many things I want to get to in this lecture. But this one is actually kind of interesting. If you think of the form of the logistic function, which looks kind of like this, where this is 0 and this is x, and this is our logistic function of x, right? And of course, the output of the logistic function I should have it kinked down, ranges from 0 to 1. And when x is 0, the logistic function is 0.5, right? I didn't draw this perfectly. But if you think about it, when the weight's small, well, actually, let's be careful. The function is this. Suppose we just have one input to our logistic function. So when this weight is small, let's say x varies from a to b, whatever a and b are, I don't care. If I make the weight small enough, then wx will only vary a little bit. This is ws. Wx will only vary a little bit, maybe from here to here. And that means my logistic function will only vary from here to here. And at that point, the logistic function is nearly linear. The second derivative of the logistic function is very small at this point. And so the function is almost linear. And so if I have very small weights, basically I'm turning my neural network into a linear regression function. Because, well, let's see. I have the input layer. Of course, that'll be linear, by the almost linear by the argument we just said. But then I have this second function, which will also be linear. That's the second layer. But a linear function of a linear function is a linear function. So one of the kind of insights into neural networks and why they are pretty useful is that when the weights are small, and remember we typically initialize all these weights to values close to 0. When the weights are small, basically the neural network is a linear function. But as the weights get larger and we get to this more nonlinear part of the logistic function, if we make the weights larger, then wx, even with the same x's, wx now can range across this much more nonlinear part of the logistic function. And so when weights are small, the neural network sort of becomes a linear function with low VC dimension. When the weights are large, it becomes increasingly nonlinear with a higher VC dimension. Remember that decision surface that we looked at for the speech recognition network? Much higher VC dimension than a linear function. And so the magnitude of the weight vector is related somehow to the VC dimension of the class of functions that the neural net can represent. And so, by doing regularization and squeezing and putting a prior, saying that those weights are likely to be close to 0 according to our prior, what we're saying is, unless the data argues with us, we're going to go with a linear function or something close to linear. And the more the data demands it, by the other objective term, sum of squared errors, if we can't get a good sum of squared errors with the small weights, then of course we'll pay the price of w squared in the objective function in order to minimize that sum of squared errors. So there's this kind of nice inherent trade-off. As you increase the magnitude of the weights, the network becomes capable of representing increasingly nonlinear functions. So it's kind of a nice, smooth thing. Okay, so as I said, there are a lot of things to talk about here, but let me jump ahead to, well, let me start here. We are going to end on time. Is there anything we know theoretically about what functions neural networks can represent? Yes, we know these kinds of things. So, for example, every Boolean function can be represented by a neural network with a single hidden layer. So sometimes people wonder, well, how many layers should I put in my neural network? It's a good question. It's interesting to know that any Boolean function, that is, if our vector of x's are all Boolean variables and our vector of y's are all Boolean variables, then any function you can define over those Boolean variables can be represented by a two-layer neural network. If any of you are electrical engineering majors, you probably have seen this result before in a different vocabulary, where people have pointed out to you that you can design a circuit for any Boolean function that has just two layers of AND and OR gates. Actually, NAND and NOR gates. Which is a big deal in circuit design because you want to make the depth of your circuit small so that it'll be fast. But this is basically the same result. So you can, two layers of Boolean circuit, primitive Boolean circuit components implement any Boolean function. And you can certainly represent with a threshold unit, a logistic function, you can represent a NAND function and a NOR function. And so you can build. But unfortunately, it doesn't say anything about how wide your circuit might have to be or your network. And in fact, it can be as bad as exponential in the number of inputs. Similarly, for continuous functions, every bounded continuous function, so even if these aren't Boolean variables but real valued variables, every bounded continuous function can be approximated with arbitrarily small error with one hidden layer. And any function you can do with two, even if it has crazy discontinuities. So it is kind of interesting. You don't need to have that deep, as long as you're willing to go wide, a network structure.
So the output of the sigma units are bounded between 0 and 1. So how would you approximate a function that will be on this bound?
Ah, very good. So you can't, when I say, that, if you didn't hear, the comment was, but the output of a threshold unit is between 0 and 1. So how can you represent any function? You can't. But if you rescale it to 0, 1, you can. So it has to be a function that can be rescaled.
If the function itself is not bounded, you can't scale it.
That's right. If it's an unbounded function, then you can't. But I mean, if you had like an exponential function, and you say, well, but my x's only range from a to b, then you can say it's bounded, and I'll scale it accordingly. But it's true. If it's truly unbounded, you can't do it.
But you can feed it into another sigma function. So to make the function you are going to approximate lie between 0 and 1, and then approximate that one.
Maybe that would be a better strategy, right? Yes?
Please give us a quick idea of when these neural networks perform better or worse than the other methods we saw before?
Yes, good question. So can I give you an idea of when these work better or worse than other things? Compared to the approaches that we've talked about so far in class, I think if you were going to train either of the first two functions that we talked about, the speech recognition function or the control of the vehicle based on image input function, I don't think any of the other functions, any of the other approaches we've talked about so far would compete very well with a neural network. The reason is, think about the highly nonlinear decision surface that we're dealing with. So that's what's really important here. Now, we will end up talking about support vector machines and kernel-based methods in about 2 weeks. And we'll see that they have a lot of the good properties of neural networks as well, in terms of being able to represent highly nonlinear functions. So I won't go as far as say that they're the best for these methods, but they're the best among the algorithms we've looked at so far.
Also, there is a question of whether the output is discrete or continuous.
Yeah, and these can be used for either discrete or continuous.
Yeah, but if the problem is formulated in a continuous way, then neural networks are almost a direct choice.
Yeah, neural networks, it is a regression problem we're doing here. So it's appropriate for continuous value things. And the usual way of having regression approaches deal with discrete value variables is just to do this 1 of n encoding kind of thing that we saw for the phonemes. There was another question?
So even unbounded functions, you can rescale it, for example, using the logistic function.
That's right. Right. So if you rescale your unbounded function, then you could. But it does take that.
Yeah, but that changes the measure of error.
That's right. That's right. So I have to be a little careful about that statement. Okay. Let's look at one more thing. And I think we may actually continue. There are a couple other things I want to get to in neural nets. But let's look at what I think is the coolest thing about neural networks. And in fact, this lecture is the beginning of a small sequence of lectures we're going to do that get at the question of learning representations. So to start thinking about this, consider this very simple neural network. There could never be a simpler one. Has 8 inputs, has 8 outputs, has 3 hidden units. These are logistic units. And I want to train this network on this set of training data. So I have 8 training examples. And you'll notice that for each of those training examples, the output equals the input. So it's the identity function. Okay, now my question to you is, can that neural network learn this function? Can it fit this training data perfectly? Almost perfectly?
Yes.
Yes. Okay, why? Because there are only 3 middle units there.
So the way that I thought of that was that I could say that the first one is 1, 2, 3, 4, 5, 6, up to 8, and then the 3 layers could code that as 0, 0, 0, 0, 0, 1, 0, 1, 0.
Good, good. So you're suggesting if you got to do it by hand, you would just make those 3 hidden units be the Boolean encoding of the digits 1 through 8. So it would be 0, 0, 1, 0, 1, 0, etc. So if you train this network using the back propagation algorithm, indeed, it does learn those. And if you look at the values of those 3 hidden units, once you train, these are the values that you get, at least in one training of the system. And if you look at it, it's doing exactly what you're suggesting. So it's basically, if you round up or down, this first input, once the network is trained, when we give it this first input, the hidden value encoding of it is essentially rounding up and down. This is a 1, 0, 0, whereas the second one is a 0, 0, 1, etc. And if you look at those are indeed, if you round up and down, the 8 Boolean, the 3-digit Boolean code for 8 digits. So what's interesting is this network is learning the Boolean encoding for 8 inputs as an efficient way, as the way to encode the inputs so that it can minimize its sum of squared errors for predicting the correct output. So in a way, we've tricked, maybe, the algorithm into learning a re-representation of the input that is sufficient for the prediction task that it has to do.
So is this hinting at a way to calculate the minimum number of hidden nodes you'll need?
I see. So you want to know what's the minimum number. Could you represent it with 2?
Probably not.
It gets hard to answer that question because if they were Boolean hidden units, then of course the only way to represent 8 things, they have 3 Boolean things. But these are not. These are continuous hidden units. And obviously 2 real numbers can easily represent at least 8 points in a two-dimensional plane. But now we get into the question of whether logistic functions can represent that code. So, and I don't even know the answer to that. So if somebody figures that out, let us know. But really, the overarching point, the point that I'm trying to get to here is, this is what I mean when I say I think of neural networks as a way of learning representations. You know, that's really hard. We don't think of computers as learning new representations of data, but that's exactly what's going on here. And so I think that is a kind of interesting, I have time to show you one more of those. So here's a neural network that is trained to take an image as input and produce as output what direction is this person looking, left, right, up, or straight. And again, it takes 960 inputs, because each of these images is just a grid of 30 by 32 pixels. So we just turn that into 30 times 32 inputs to the neural network. Has these 4 outputs, which are, you know, coded with all zeros and a 1 to indicate, in this case, the person's looking straight ahead. And when we train this network, it's 90% accurate, predicting which of these directions people are looking. These, by the way, are people in an earlier machine learning course, all of whom were subjected to sitting in a chair and being photographed with sunglasses without, smiling, frowning, looking in different directions, etc. And that data is available if you want to use it for your project, for example. Several of these people have gone on, like Amy here, went on to become a professor. Great people. Anyway, once this network is trained, we can do the same thing. We can look at the hidden unit and ask, just like in that case of Boolean coding of the 8 digits, what's being learned. Here are the weight vectors going into the 3 hidden units. So this is hidden 1, 2, 3, going into them. And here are the weights going into the output units from those 3 hidden units plus a constant. So, you know, just like when you train your logistic function, we can put in a constant, a W0, which corresponds to constant 1 input, just for a bias term. And what's interesting about this is obviously these weight diagrams, and again, a white means a high positive weight, black means a high negative weight. These things are obviously kind of ghostly, face-like images. So they're capturing some structure of that image, even though, of course, they're not told what the geometry of the image is. It's just a vector of inputs to the system. But if you, for example, look at, let's look at hidden unit 2. Yeah, let's look at hidden unit 2, which has a lot of white over on the left side and a lot of black over on the right side. So that activation, that unit is going to be activated on the left side, your left. So if I look this way, my white skin is here, my darker, not that dark, hair is back here. And so that's going to activate this unit a lot, because the white skin multiplied by the high positive weights, that's going to be a big positive number. The dark hair, which is a low intensity, times the negative weight, that won't have much of an effect. Whereas if I look the other direction, then I'll be the white skin and the black weights will make it a big negative thing. So this thing is going to be sensitive to whether the face is looking left or right. And indeed, hidden unit 2 has this weight to the right-looking output and this weight to the left-looking output, and not much impact on the straight-looking output. So if you think about it, it's, again, learning some re-representation of the input, complex 30 by 32 images, boiling it down to just 3 numbers, 3 real-valued numbers, which encode not everything about the image, but the best stuff that you can encode about the image, the stuff that will minimize the sum of squared errors in predicting these 4 output features that we're trying to predict. So it's not just a matter of re-encoding the input, it's re-encoding it with a purpose, where the purpose is to minimize, to optimize the fit to the training data. So let's stop with that slide. And we're going to continue this idea of looking at machine learning algorithms. We're going to look at a category of algorithms people call dimensionality reduction algorithms. You can think of this as the first one we've encountered. It makes very good intuitive sense. But this idea of getting computers to learn to re-represent input data in a more compact and still informative way for the task we have in mind is another one of the key concepts in this course. So we'll be talking about things like PCA, latent variable models of different types over the next couple lectures. By the way, I just wanted to say I have to leave town right after class, so today I won't have my usual office hours here.